Okay, so and also some of our previous meeting origin seminar talks have not yet been uploaded to YouTube channel, but it will be soon. I apologize for that late uploading. So today, before we start Noah's talk, I would like to remind you to please keep yourself muted during the meeting unless you are speaking. And if you have an important clarification question, please raise hand in participant list before you ask. Or you can also type a question in chat. For the clarification question will then be the question for you. So then today's speaker is Noah Tuchow. He's from Penn State University as a graduate student and working with Jason Wright about habitability. So we'll hear from Noah about the potential habitability as a stellar property, assessing the habitable histories of stellar systems. So Noah, the floor is yours.
Okay, thanks for that introduction. So a bit of a disclaimer, my computer is having some somewhat major graphical problems right now, so hopefully my computer won't crash in the middle of this talk, but if it does, I might need to reconnect. But yeah, so my research is on the potential habitability as a stellar property, assessing the habitability of stellar systems, and I'll explain what exactly I've been doing for my research, for my thesis research. So So the motivating question for my research is what type of stars are the best targets for a search for biosignatures? So there's several different types of stars that we could potentially envision ourselves looking at. I'm going to list like a bunch of random types of stars. Some of these will be good types of target stars, and some of these might be really, really bad target stars. So an example would be, and when I list these possibilities, I want you to think whether or not you have the implicit assumption whether or not this is a good target star or a bad target star. So we could think about young flaring M dwarfs, blue hypergiants, solar analogs, white dwarfs, old K stars, red giants, or brown dwarfs. So as I listed those types of stars, you probably have a qualitative understanding about which of these would be a good target to look at if you want to find biosignatures. So we typically prefer some like FGK stars, and we also prefer older stars, given that it took around 2 billion years for photosynthesis to develop on Earth. We don't typically prefer massive stars, giants, neutron stars, and white dwarfs due to their potential obstacles for habitability. So the motivation in my research is I want to find a way to quantify and formalize this intuition. So my talk will be organized as follows. First, I'm going to talk mostly about the time dimension of habitability. Then I'm going to start talking about how we go from habitability to detecting biosignatures. And finally, I'm going to talk about the application to direct imaging missions, future direct imaging missions. So let's first talk about the time dimension of habitability, or habitable histories of stars. So most astronomers are familiar with the concept of the habitable zone, which is the range of distances from a star where Earth-like planet could support liquid water on its surface. The classical habitable zone typically assumes that CO2 and water are the dominant greenhouse gases, but there are many different formulations of the habitable zone. Important for astronomers is that the habitable zone can essentially be thought of as essentially can be easily calculated by given the luminosity and effective temperature of its host star. So the habitable zone only really gives a snapshot in time. It can tell you which planets are likely to have liquid water on the surface at a given time, but it doesn't necessarily tell you the entire picture. So we've had the terminology that we refer to the habitable zone in the current day as the instantaneous habitable zone. But there's a problem in that planets in the current day habitable zone could have stayed there for billions of years, or they could have just entered it. So stars evolve and change in time, and as they evolve, so too do the habitable zones. So over here we have a figure of the habitable zone evolving as a function of time. We have distance on the x-axis and age on the y-axis. And we can see that the habitable zone moves outwards. This is for a solar analog, so for some like star. And we can see that there's a region of the habitable zone that's stayed continuously habitable, but there's also planets that entered the habitable zone after its formation, or after their formation. So we can essentially come up with different classes of habitable planets based off of the star's evolutionary history. So there are continuously habitable planets which have stayed habitable since their formation. And then there are belatedly habitable planets, which are planets that have entered the habitable zone from outside as their star evolved. And of these belatedly habitable planets, there's actually two subclasses of them, which are inner belatedly habitable zone planets, which are planets that originate from within the inner boundary of the habitable zone and enter as the star potentially becomes dimmer. Then there's the outer belatedly habitable zone, where planets from outside the outer edge of the habitable zone, which enter it as the star becomes more luminous. Sometimes these outer habitable zone planets, or outer belatedly habitable zone planets, are referred to as cold starts, but that term has since become a little bit ambiguous since there's also another term, cold starts, in the context of giant planet formation. So we'll mainly refer to these planets as outer belatedly habitable zone planets, which is a little bit mouthful, but it's less confusing. So the relative sizes of the region of the habitable zone, which are occupied by the different classes of habitable zone planets, depends on stellar age and mass. So this figure over here, we can see that this is the habitable zone evolution of two different stars, a 0.5 solar mass star and a solar mass star. And these two lines are given. These two lines give the inner and outer boundaries of the habitable zone. And we can see that as the star evolves, different regions correspond to different parts of the habitable zone. So the continuously habitable region gradually shrinks in time, whereas more and more planets enter these belatedly habitable regions. So for the low mass, a 0.5 solar mass star, most of the planets have entered the habitable zone from within the inner edge, due primarily to the dimming on the early main sequence of a low mass star. Whereas for the solar mass star, we can see that there's a larger continuously habitable region, but as the star evolves, more and more planets enter from outside. So why is it important to consider this belatedly habitable zone or belatedly habitable planets? So many, if not the majority of planets that we find in the habitable zone, will belong to this class of belatedly habitable planets. So we want to know essentially what portion of habitable zone planets are in the belatedly habitable zone. And this depends, and this depends among other factors on when we consider habitability to start. So in order to consider where habitability starts, you want to know about the onset of plate tectonics, the delivery of volatiles, and other geophysical processes. So these plots show the fraction of planets in the belatedly habitable zone as a function of host star mass and age. This a star over here represents the solar values. And so for the sun, around half of planets are in the belatedly habitable zone. The other half are continuously habitable. And we show two scenarios for different starting times for habitability. If habitability is assumed to start at 10 million years, i.e. volatiles are primarily delivered from the protoplanetary disk, then one would assume that 75% of planets will be belatedly habitable planets. However, if we assume that habitability starts after, say, 100 million years, then only around 32% of planets, which is still a large number, would be belatedly habitable planets. And this could potentially be a scenario if the majority of volatiles are from impacts or late Vernier, late Vernier accretion. So the fraction of planets that a given star has in the belatedly habitable zone depends on when habitability is considered to start, as well as the mass and the age of the host star. And one should not assume that these belatedly habitable planets are habitable just because they fall in the current day habitable zone. So we want to know whether belatedly habitable planets can actually be considered habitable. So there are potential obstacles to habitability for both subclasses of Belatedly Habitable planets. So for planets entering from for planets entering the habitable zone from interior of the inner edge, there's a problem that a lot of these may be desiccated planets that have been depleted in volatiles due to them being subject to high stellar UV fluxes, etc. And this is particularly an issue for low mass stars, which can spend hundreds of millions of years contracting and dimming before they settle on the main sequence. However, recent research suggests that it might be possible to retain volatiles during the extended magma ocean phase on these planets, so they could potentially keep a reservoir of volatiles within the mantle. So outer Belatedly Habitable Zone planets have somewhat opposite problems. These planets are thought to potentially be globally glaciated, similar to the type of snowball Earth state in Earth's early evolution. So these planets would have the problem that they'd have high ice albedo, and this would make them very difficult to melt. And in fact, some studies have shown that the flux required to melt these may in turn directly lead the planet to a runaway greenhouse effect. So you might end up having so much flux that you boil away all the water. Okay, I'm having a problem. Okay, and it's also due to global ice coverage and due to global ice coverage, it may be difficult for such planets to outgas a thick enough atmosphere. So we have several open questions about this class of planets. Can Belatedly Habitable Zone planets be considered habitable? When should we consider habitability to start? What are the timescales for the onset of plate tectonics and delivery of volatiles, essentially the onset of habitability? And how does the ambiguity of habitability of Belatedly Habitable Zone planets affect the search strategies for future missions to image Earth-sized habitable zone planets? And will these future missions be able to empirically test the habitability of this class of planets? So we've defined this class of Belatedly Habitable planets, but we're not really sure they're habitable. So we want to essentially go from knowing the habitability of the planet to searching for biosignatures and dealing with this ambiguity of the habitability of these cold star of these Belatedly Habitable planets. So just knowing if a planet is part of this class of planets, like if it's Belatedly habitable or continuously habitable, doesn't really tell us how long it's spent in the habitable zone. To search for biosignatures, we essentially want to find planets that have been in the habitable zone for a extended period of time. Life on Earth took around 2 billion years to produce oxygen as a biosignature, and it took around 4 billion years for oxygen levels to become high enough to actually be detectable. So we define this quantity we call the habitable duration, which is the time spent in the habitable zone as a function of the distance from the host star. And so this is from a solar analog. So this is from a solar analog at the current day. We can see the distances that a planet spends in, the durations that a planet spends in the habitable zone as a function of distance from its host star. So we can see this plateau region is planets that have spent the full duration of their host star's lifetime in the habitable zone, continuously habitable planets. And then this outer region is planets that have entered it from outside. Here we use the term cold stars, but these are outer Belatedly Habitable Zone planets. And these red regions are regions that are outside of the current day habitable zone. So this curve is only for a fixed moment in time. This gives you the time which a potential planet would have spent in the habitable zone. But we can see how this curve essentially evolves in time. So the curve starts off relatively wide with a large portion of planets in the continuously habitable zone. And as the star evolves, the planets in the continuously habitable zone spend more and more time in it, but like the inner edge recedes and more planets enter it from outside. So you get this kind of larger tail on the curve and a taller continuously habitable zone. So as it evolves, you see this type of trend. And the area under this curve might actually be a useful quantity for determining the long-term habitability of a given for determining the long-term habitability of planets around other stars. So we've come up with a general form of metrics to infer whether or not a planet, to infer whether or not a star would be a good target for searching for biosignatures around. So this is this quantity B, which is the integral of two quantities, H and gamma. I'm going to define what these are. Gamma is the distribution function for planets as a function of center major axis and radius, whereas H is the probability of biosignature emergence as a function of distance and time. So as you may have already noticed, neither H and gamma are particularly well known, and they lack empirical constraints and depend on our models and our hypotheses. Sorry, I'm just trying to, my screen is a little bit, science getting in the way of it. So for gamma, one can use any realistic distribution for planets in the habitable zone, such as an extrapolated power law or empirical constraints. And so here we'll just consider contrasting forms of gamma, which is gamma uniform in A, which is just an example of what happens to a different distribution gamma, and uniform in LNA, which is similar to like Bode's law, which is relatively more physical. So H can incorporate how long planets maintain their habitability throughout the evolution of their host stars and luminosity and temperature. And it's essentially pretty model dependent. It's not very well constrained, as we only have one case of biosignature emergence, but we have a lot of assumptions and models about how biosignatures might emerge. So we have several options for what we could choose for H. We could assume that all planets in the current instantaneous habitable zone have the same chance of hosting biosignatures. This is a pretty naive assumption, but it's often implicitly assumed. We could assume that the probability of biosignatures emerging is constant if a given duration has been spent in the habitable zone. We could also assume that the probability of hosting biosignatures is proportional to the time spent in the continuously habitable zone. Or we could assume that the probability of hosting biosignatures, H, is proportional to the time spent in the habitable zone, which includes these Belatedly Habitable Planets. So we've developed a flexible framework to assess how likely stars are to host biosignatures on their planets. It depends on these quantities H and gamma. And we've given a couple examples, but realistically, anyone could use their own assumptions or their own empirical constraints on these functions in order to rank in order to rank stars based on their prior knowledge. So, and this is potentially useful for prioritizing target stars for future missions and interpreting positive results. So we will investigate how different sets of assumptions affect which stellar populations are preferred. So we find that different formulations of these metrics favor vastly different target stars. So these metrics are calculated for a group of stellar models in mass and age of the host star. And in this set of plots over here, the rows are assumptions about H, and the columns are assumptions about gamma, the planetary distribution function. And H is the emergence of biosignatures. One can observe that different assumptions lead to different stellar populations being preferred. So let's pay attention to the right-hand plots, which are the more physically motivated ones. The primary reason why we're showing these gamma uniform and A ones is primarily to show that the assumption about the planetary distribution function does have a pretty large effect, but we should just focus on the gamma uniform and LNA in natural log of A in order to get a more physical a picture about which stars we prefer. And so when you see that these top columns, which are these top rows, which are considering the case where habitability, the probability of biosignature emergence is directly proportional to time spent in the habitable zone, either including or not including these Belatedly Habitable planets, one can see that it replicates our assumption that older, potentially a low mass, around K stars would be the dominant, would be the best candidates to search for biosignatures around. Whereas if you just assume that the width of the habitable zone is what matters, then you end up having these like really misleading assumptions that you'd assume that the most luminous, like the largest and the most evolved stars, have the largest habitable zones and the highest probability of posting biosignatures, which should not be a good assumption. So one can see that considering the duration spent in the habitable zone has a major effect about which population of stars is preferred. So now I'm going to talk about how these metrics can potentially be applied to direct imaging missions. So the metrics that we've developed are able to rank stars based on the potential to host planets with long-term habitability. And future missions aim to obtain the spectra for Earth-sized habitable zone exoplanets. There's different methods about doing this. There's spectroscopy, but what I want to focus on right now is direct imaging. So direct imaging is actually looking directly at a planet around another star and measuring the spectrum from that planet's light. So future missions want to determine the atmospheric compositions of Earth-like exoplanets and search for biosignatures. And we suggest that our metrics might be useful for target prioritization. So direct imaging is potentially the best way how to get exoplanet spectra, but why aren't we doing it right? But why isn't it always being used? So the main problem is that direct imaging has several obstacles which are difficult to overcome. So the first main obstacle is that stars are really, really bright, and that you need to mask them, and that we need to mask their starlight with a sophisticated coronagraph. And the second, a somewhat obvious problem is that planets are really dim, and so currently larger and younger planets are easy to detect, and also planets that are farther away from the host stars. Additionally, there's the problem of exozodiacal light, i.e., there's dust in these stellar systems that scatter light and add a background amount of light that can be make it difficult to attain planetary spectra. So all these concerns for direct imaging may require really, really long exposure times to obtain a usable spectra for Earth-like planets. So future direct imaging missions are being designed to potentially mitigate these problems. So currently, direct imaging is limited to far-out giant planets, but these future missions want to extend the capacity to include Earth-sized planets in the habitable zone. And this requires a very sophisticated coronagraph and a sophisticated telescope. So in the 2020 Decadal Survey, there are two proposed exoplanet direct imaging mission concepts. There's HabEx, which features a 52-meter external star shade to block out the star's light, and image the planet's light, and it has a 4-meter diameter telescope. Additionally, it also has an internal coronagraph and a UV spectrograph. There's also LUVOIR, which has two potential architectures which are being proposed, which there's a 15-meter LUVOIR-A and an 8-meter LUVOIR-B. And LUVOIR is special in that it has a wide wavelength coverage, that it covers wavelengths in the UV, the optical, and the infrared. And this mission uses a sophisticated internal chronograph rather than external star shade. So these missions aim to image Earth-like planets in the habitable zone of their stars, but even with the sophisticated instruments that are being proposed for these missions, they're still limited to nearby bright stars. So these missions need to select target stars to observe the maximum yield of Earth-like planets. And we argue that target selection should also consider stellar evolution and how long planets stay habitable. And our metrics could potentially be useful for this target prioritization. So we would like to rank stars according to our metrics, but we want to know how exactly. So we want to know how precisely can we determine the values of these metrics for a given star, and how precisely can we rank stars according to each other. So there's two main sources of uncertainty in our metrics. There's systematic uncertainty, which comes from fitting stellar models to observations, and then there's uncertainties in the stellar models themselves. So we'll give a brief overview of what we're currently doing in our ongoing sensitivity analysis. So let's first start with model uncertainties. So stellar models give the host star's evolutionary track and used to calculate metrics. We essentially, so we fit a model to observations of a given star. However, models often contain uncertain physics and models may conflict with each other. So there's several open problems which I'm going to talk about briefly. So the first of these problems is the solar abundance problem, or sometimes more openly called the solar modeling problem. So back in 1998, using the state-of-the-art abundances back then, one could calculate the evolution of a one solar mass star and have the resultant surface properties and interior structure that match those of the current day sun. However, with a newer abundance profile of the newer measurements of the chemical abundances of elements in the stellar photosphere, solar models no longer match the sun's observed properties as well. So this appears to be an apparent disagreement between stellar modeling results and helioseismology. And this is most apparent in the disagreement between the sound speed profile and the density profile of the sun. So this plot over here, in black, we can see the old results for the 1998. So for the 1998 chemical abundance measurements of the stellar photosphere, we can see that it was much better matched for the compared to the 2009 measurements. And same thing with the density profile. So stellar models currently disagree about the abundances. There's some speculation that maybe the newer abundances are incorrect, or maybe because the newer abundances were calculated using a 3D model, whereas most stellar evolution models are one-dimensional. There could be some disagreement due to the difference in dimensionality. And so different widely used stellar models differ on which set of solar abundances they use. So which set of solar chemical abundance patterns they use. And there's also the speculation that maybe the opacities used in these stellar model calculations could be incorrect. So in a laboratory setting, we observe that ion opacities are higher typically than what's used in stellar models. And so there's a lot of different stellar models that vary in the opacities and the equations of state which they use in the interior. There could also be a problem with the treatment of convection, in that most stellar models are one-dimensional, and convection is kind of a uniquely three-dimensional problem, so we have to resort to a 1D mixing length theory, which may be inadequate to actually match the 3D atmospheric results. And it's unclear how to handle problems like convective overshooting. So furthermore, there's some other disagreements between stellar models. They disagree in their treatment of rotation, their atmospheric boundary conditions, and then in conjunction with the stellar model uncertainties, there's some uncertainties that are a combination of stellar and planetary model uncertainties. So such things are such as like the faint young sun problem, where we have evidence that Earth had liquid water very, very early in its history, but current models say that the sun would have only had around 70% of current luminosity. So one would expect Earth to have been too cold back in the distant past. But this problem is potentially solved by having a thicker atmosphere or different greenhouse gases present on the early Earth. However, the warm early Mars problem is a major problem in that models say that Mars shouldn't have been warm enough in the past to support liquid water, but we have strong evidence that it did. This either requires a reevaluation of most atmospheric evolution or a reevaluation of solar evolution. So how do we determine the model uncertainties for a given star? And the model uncertainties in determining these metrics and other properties for a given star. So there's hundreds of models parameters to vary. And it's not really feasible to determine the sensitivity to each model parameter individually. So instead, we'll use the methodology of Tayara et al. 2020, and we'll compare the results from 4 well-established stellar models with different input physics. These stellar models include the Yale Rotating Evolution Code, the MESA Isochrones and Stellar Tracks, MIST, the Dartmouth Stellar Evolution Program, and the Garching Stellar Evolution Code. And we'll calculate our metrics for each model grid and see the differences between our models. So this plot over here, these two sets of plots are looking at one of our metrics where the probability of biosignature emergence H is linear in habitable duration, including these Belatedly Habitable planets, and gamma is uniform in LNA, which is close to what you'd expect, like for any standard power law distribution of planets. And so this plot over here is a contour plot which shows the value of this metric in solar units. So 1 represents the value for the sun, and we're plotting the mass of the host star. And this quantity is a little bit difficult to understand. This is EEP, which is the equivalent evolutionary phase of the star. So stars at 200 will have just entered the main sequence, whereas stars at 450 would have entered the terminal age main sequence, and stars at around the 600 and enter the end of the subgiant branch and reach a helium flash. So the different panels show the results of these different models, and one can see that you expect the highest values for low mass stars on the main sequence, and we've also cut it off at so we've masked out values that are greater than we've masked out values that correspond to ages greater than 10 gigayears to primarily stars that would drown our galaxy. And of these stars that we'd find, we would think that the lower mass stars in the early main sequence are potentially like the oldest lower mass stars would be the best candidates according to this metric. However, there's pretty large disagreement about these contours of age between these different models. And so we can see the differences in the metrics in this plot. And we see that there's a large difference for these. So for the stars that have the best probability of hosting biosignatures, we can see that there's a large disagreement about them, primarily because there's a large disagreement about the ages of these low mass stars. Additionally, there's also another disagreement about stars on the subgiant branch, where the different models disagree about how quickly they evolve at different phases. So we obtain, and so that's how we're obtaining model differences, and then we want to focus on systematic uncertainties. Essentially, we obtain masses, ages, and values of our metrics by cutting stellar models to observables, and we would like to know what precision to and so we would like to know the precision to which we can determine our metrics for a given star, and how does improving the measurement precision and certain properties affect the precision of our metrics. So we start with a model of a solar analog observed from 50 parsecs away, and we fit stellar models to observed properties such as effective temperature, FE/H, log G, Gaia band magnitudes, and parallax. And we use a traditional set of standard uncertainties for each parameter. So those are listed here. These are probably like some of the best that we could get with the current generation of instrumentation. And so we run MC change to determine the uncertainty in the derived parameters such as stellar masses, ages, and also the values of our metrics. So we scale the uncertainty in each observable, and we determine how it affects the uncertainty in these derived parameters such as our metrics. So these plots over here show the uncertainty in observed properties and how it relates to the uncertainty in derived properties. So this subplot over here, sorry, my mouse has disappeared. This subplot over here, we can see that we've scaled the uncertainty in all of the parameters, and we can see a somewhat obvious result in that the total uncertainty in we can see that the uncertainty in all these different parameters, these 3Bs are different metrics, and there's mass and age also in here. And we can see that it scales relatively linear in log space as you decrease the total uncertainty. However, it's not necessarily feasible to get down to these levels, or it might not even be physically possible to get down to some of these levels. And so we're looking at specific parameters. We can see that the metrics are potentially more sensitive to certain properties, such as effective temperature, than they are to others, such as FV on H. And there's somewhat of a medium sensitivity to log G. But if you were able to determine T effective really precisely, say down to like 10 Kelvin, then you could potentially get pretty high precision in metrics for some like star. So now we're comparing both the systematic and model uncertainties, and we're considering 3 different stars at similar evolutionary phases of different masses. So we've got sorry, my zoom is in front of the figure, so I can't really see it that properly. Yeah, so we have a 0.7 solar mass star, a 1 solar mass star, and a 1.25 solar mass star. And one would implicitly assume that the lower mass star would rank highest according to our metrics, and that the stars of increasing mass would be increasingly worse targets. And that's somewhat what we observe in this plot. So we determine how well each of the 4 different stellar models can recover the true values for these simulated stars. So we've simulated these stars where we know the true values of all their derived properties, like their masses and ages, and also the values of our metrics. And we're using MCMC chains to see if we can effectively recover the true values from these models. And let's pay attention first on these field markers, which are the values from only isochrone fitting. And one can see that the isochrone fitting doesn't do that great of a job of actually recovering the true values, at least for some of the models. I mean, I guess MIST does a decent job. And so these different columns are the different models, and these icons over here are the values with error bars. And we can see that there's very small error bars for some of the other stars, but for the low mass star, there's pretty large error bars to an extent that over here, it's a little bit ambiguous whether or not the 1 solar mass star and the 0.7 solar mass star, which one is a better target. So isochrone fitting alone can typically constrain the more massive or solar mass stars. So we can see that it's easy to tell whether or not the 0.25 solar mass star or the 0.1 solar mass the 1.25 solar mass star and the 1 solar mass star, which one of them is a better target. But the 0.7 solar mass star varies pretty widely between models and also systematically within a model. So with these unfilled markers, we show the results of adding a 10% constraint on age, which is very difficult to obtain model-independent age constraints. I mean, it's somewhat possible with gyrochronology methods, but it's very difficult. But we show that if you have a 10% age constraint, then you can get much better both agreement with models and lower systematic uncertainties. So you can much more easily recover the true values. So it's recommended for lower mass stars that like potentially age constraints could improve our precision for lower mass stars, but as I said before, it's pretty difficult to obtain them. So the major findings of this research are that our framework allows biosignature emergence to be quantitatively connected to target list prioritization. This means that different assumptions about biosignature emergence and a distribution of rocky planets will affect what population of stars are preferred in a search for biosignatures. And stellar age is potentially the most important factor in predicting which stars have the highest chance of hosting planets with biosignatures. And obtaining model-independent age constraints is difficult, but they're especially important for low mass stars. So what are the next steps for this research? So belatedly habitable planets, as we mentioned, are a rich area for future research. They make up a large fraction of planets in the habitable zone, but the habitability remains pretty ambiguous. So we plan to model belatedly habitable planets, observe what features might be detectable in the atmospheres. And we want to determine the statistical power to which one can empirically test their habitability. Furthermore, our research puts us in a good position to rank these direct imaging target stars according to our metrics. This would potentially require us to more accurately determine the masses and ages of these stars, as a lot of the field stars don't have well-constrained masses and ages. So its potential project would be obtaining all the masses and ages and also values of the metrics for direct imaging target stars. So with that, I'll ask for questions, and thanks everyone for having me.
So thank you very much, Noah, for giving your talk.
Sorry if I was
everybody
stumbling over myself a little bit. I can't really see my slides, so I was trying to remember what I was saying in the slides.
Are there any questions? You can either raise your hand or you can type it in the chat. There's a question from Dan.
Oh.
Hey Noah, thanks for a really nice talk. It was very interesting. I was wondering, one of the things that determines how well stellar models do is the metallicity itself. So we know that the models get worse as you move away from solar metallicity. Yeah. But we know that metal poor stars actually can, host rocky planets, and we have examples for this. So have you looked into that dimension? How worse does it get with your metrics if you move away from solar metallicity, or was that part of your parameter?
We varied metallicity as a free parameter. We haven't really looked at we haven't really looked yet at how departing far from solar metallicity will affect the precision of the metrics, but that's an interesting question. I imagine there would be a higher model disagreement at non-solar metallicity levels at potentially really low metallicities or maybe really high metallicities. So we primarily focus on comparing models at solar metallicities, but it would be interesting to see how the models differ at different metallicities.
Yeah, they should do best at solar metallicity, but yeah, I mean, we would hope that at least in the solar neighborhood, that
a lot of this has been using isochrone grids, and if you look at isochrone grids, a lot of them are pretty roughly sampled in metallicity. It's like whether or not you're even sampling something that a stellar model would give if you ran it at that metallicity is ambiguous. It might just be an interpolation effect.
Yeah. Anyway, great talk again.
Yeah.
Thanks.
Okay, so I also had a question.
Sure.
You mainly targeted heavier stars because you're working for direct imaging missions for space like LUVOIR, but ground-based telescopes, they will also do direct imaging observations of exoplanets, but that's more around M-dwarf and really low mass stars. So how low mass have you pushed your analysis?
So let me for this plot. So I think we've only really gone down to 0.6 solar masses. So we haven't gotten down that far yet. We're planning to do something more for M-dwarfs and stuff, but we haven't really gotten there yet because M-dwarfs have their own obstacles to habitability and tidal locking, and we haven't really incorporated that in our models yet.
Okay, thanks.
So one could potentially use a different model for biosignature emergence for an M-dwarf because of the obstacles to habitability.
I can see that Serena also has a question.
Yeah, it's connecting to the lower mass objects. So when you go below the 0.6 that you tried, another difficulty would be, I guess, the uncertainty due to stellar models.
Yeah.
Did it actually was it part of the problem that you didn't try that lower than 0.6 as well?
So part of the reason why I didn't go below 0.6 was because the tabulated model grids that we were using stopped there. So we would actually in order to go lower than that, we'd have to use potentially a different set of model grids to identify model uncertainties because I guess not all stellar models are applicable to all mass regimes and stuff. So we were using like different model grids. Let me go back to this slide. So like 0.6 solar masses is the common denominator for all of these go down to that level and stuff. Some of these go down much lower than that, but other ones don't go lower than that. So we would eventually want to compare different stellar models if we're going to really low mass stars.
I see that Daniel has a question.
Hi, Noah. Very nice talk. I had a question about obviously another interesting component here is the evolution of the planet. So if you consider a system in which a planet is currently in a habitable zone, but it was previously not in a habitable zone, you could imagine that there were multiple evolutionary pathways that converge, basically possible pathways that converge in the present state. So if you look back, just multiple paths are possible past for the planet. So how do you see that there is a way to constrain which was the starting condition of the planet, or which was the evolutionary path that led to a planet as current state in the habitable zone, and how would you go about constraining those?
So we've primarily been constraining the stellar evolutionary paths as opposed to planetary evolution. But yeah, if you have enough observables about the star, you can break the so the problem, if you only have a few observables for the star, is that you have a lot of degeneracy in potential evolutionary paths, which could lead you to a certain place. But if you have a lot of measurements, such as surface gravity measurements and surface Fe on H measurements, that's much easier to break that degeneracy to actually get a unique path that gets you to your current cellular location. As for the planetary evolution, I haven't considered the planetary evolution aspect yet, but I'm hoping to model that in the future so we can see exactly like what the effects of different stellar evolutionary paths have on the planetary evolution.
Yep. Okay, thank you.
Everybody can applaud if they want. Yes, that brings us to the end of today's Origin seminar. And I welcome everybody again to come again next week. And I hope to see everybody there. Thank you.
Yeah, thank you.
Thank you.